being a parameter of a population. An example that we might be interested in is, for instance, computing the mean income for all U.S. citizens in 2020. In order to calculate this value, we'd need to actually have the income values for every single person who's a citizen of the U.S. in 2020. Often, you really don't have that. Um, you have instead a sample, a random sample from the population. And in this case, if we had, say, 5,000 people in the sample and we had all their incomes, then what we might be able to do is take the mean of the 5,000 people's incomes and use that as an estimate for our parameter, an estimate for the mean income of a US citizen in 2020. This is just an estimate of the parameter, and we should be careful to note that this estimate depends on the random sample that we took. Let's move over to look at some actual income data using our IPython notebook. Here, we'll load the table SF, which imports data from the file San Francisco 2015. This is data about the San Francisco City employees, and it contains an awful lot of information. For instance, the department code of the person of where the person works, the union code for them, and in particular, it contains their salary, overtime pay, other salaries, total salary, etc. There's benefits information, and in the end, there's total compensation. That's what we're going to be interested in our study. We'd like to try to understand the total compensation of San Francisco City employees. Let's check out the values for the mayor. We can filter the SF table by insisting that the job column equal the mayor string. And here's that one row. You can see that the mayor earned just under $40,000. You could sort the table by total compensation in descending order and show the top 5 earners. And maybe surprisingly, the mayor is not among the top 5 earners in the table, but you can see the chief investment officer earns about 1.5 times the mayor, and there's a number of other folks that earn more than $400,000 among the San Francisco City employees. We could also look at the bottom earners in San Francisco. Here we'll set the descending equals false tag to be true, and we'll show the 5 bottom earners, and you can see some strange things happen. These people have negative total compensation. That can happen for a variety of ways. Sometimes people are moving from one job to another, and this is really just an accounting gimmick. So we should take that into account. Let's try to filter the table and remove some folks whose salaries are just too low to seem reasonable. One thing we might be interested in is all employees that work, say, part-time or more. If you were an employee in San Francisco working, say, 20 hours a week, that's half-time, and you were earning $10 an hour for all 52 weeks in the year, you would earn $10,400 in a year, and maybe that's a good cutoff to remove all the folks that earn less than $10,400 a year. So here we'll filter the table using the where command in order to just look at employees who are working at least half-time, and we'll call the new table SF again. And there's still 38,000 or more rows in this new table, so we've got a lot of data. We could compute, say, the median the median compensation for the remaining employees here using the median command. And we can see it's just a bit above $107,000. This is a parameter. It's not a statistic. It's an actual value that's computed from the entire population of folks earning more than $10,400 a year in the San Francisco City employees database. Let's look at a smaller sample and see how that smaller sample would look. Imagine here that we don't have access to the entire 38,000 records. We need to look at a much smaller group, and suppose we sample 300 just to get 300 people from the San Francisco table, and we sample with replacement equaling false, meaning that we can't pick an employee twice. So we're getting 300 different individuals in our sample. And here's a sample like that. We could compute the median for our sample, the median total compensation for our sample, and it's very, very close to the median income for the entire population. A random sample of 300 people seems like a pretty good approximation to the entire collection of city employees. If we looked at the histogram for the entire population, it looks like this. Here's the histogram of the total compensation for the entire population. You can see this long right tail off to the side here, and that is going to pull up the mean total compensation above the median total compensation. Let's look at the histogram for our sample. It's looks like this. It's very similar. It's again got this kind of tail going off to the right, and you can see there's some small differences between them, but they seem kind of roughly comparable. Here there seems to be a spike right around 100,000, and here there's again a spike maybe around 100,000. There's maybe a little bit more folks here earning just below 100,000 than we were expecting to see. The sample that we took of 300 is a representative sample, but if we took another different sample, we might expect to see some different behavior. Let's take a different sample, and here you see slightly different behavior in the sample. Could take another sample yet again, and we could compute the median income for these two samples. One of them was quite a bit higher than the population median total compensation. Here it's higher by about $10,000. This one here looks like it's almost bang on again, right on the median for total compensation for the entire population. So sometimes the sample median is going to look like the sample, like the population median, and sometimes it's not. And that's a bit disturbing that our statistic can depend very much on the sample that we take. We'd like to get a sense of how variable that sample is, and we'll examine that in the next section.